Okay, so this is session 10. We're going to talk about the transpose algorithm.
Yes. Okay. So here we are. We're in the development version of GraphBLAS, but it is pretty much now a stable version. Again, let's see, where is it? What version of GraphBLAS? 9.3.2, which is not released yet, but it's very similar to 9.3.1. There's not a lot of changes. Okay, so I'll use the development version, but transpose hasn't changed. So
Sure.
transpose is a widely used function. Okay, if you look for, say for instance, GB transpose cast, because many of the GraphBLAS methods, there's a descriptor. It says please transpose the matrix. Now, ideally, I don't actually have to transpose the matrix. I can use it in place and operate on as the transpose. But there are places where I do need to create a transpose. So here, assign bitmap. This is a transpose, and it's doing the typecast as needed at the same time. And so um, um, so it's both transposing and casting it to the desired type, which is a one-step operation. I'm explicitly constructing a transpose here. And that's expensive. So if I also have to typecast the matrix to some required format, I might as well make a typecasted transpose at the same time. The transpose is also able to apply a unary operator, which is a cast is a unary operator. It's a kind of unary operator. So I have a thing called GB transpose op, which is used inside apply. No, where is it? It's just in transpose. Okay. Let's see. I thought I called it within the apply itself. So apply can call a transpose. Where is it? Oh yeah, it just calls transpose sometimes. So if you call GRB apply and you say apply unary op and transpose the matrix with the descriptor, I actually just go call transpose, because transpose can take an operator as input, which the GRB transpose does not do, but the transpose method does. My internal transpose, because I use it in that kind of many kind of ways. So here, for instance, I'll call transpose and this is my general method, GB transpose, and it can take an operator. And so apply will just directly call transpose. GRB transpose passes in a null operator, and it might do typecasting. So okay, so let's look at transpose is very fundamental. It's fully JITted. There is a JIT kernel. There are JIT kernels for. There's four different. Three different kernels, and inside those kernels there are different methods. Actually, in some of those kernels, I select at runtime what different methods I'm going to use. So there's different algorithms inside. In particular, GB transpose sparse. There's at least three different methods how I parallelize the transpose. Okay. So let's start with just GRB transpose, which is not the only gateway, right, into transpose, but this is the user gateway into just transpose the matrix, please. And in the GRB transpose method, there's the output matrix, there's the mask and accumulator, and all it takes is the matrix and a descriptor. But the descriptor is actually, well, the descriptor is used. The descriptor is used for the mask operation, complement structure. This you've seen before in apply, for instance. I'm parsing the descriptor from the user and I'm getting the mask from the user. It's going to perhaps return an ISO valued shallow copy. It's going to do all kinds of different things. I think we looked at GB get mask already, didn't we?
Yeah.
Yeah. So the funny thing about GRB transpose, you can pass in a descriptor that says transpose, which means don't transpose, because GRB is doing a transpose.
Right.
It's a
But there's a
dyslexics nightmare.
there's a I seem to remember there's a utility to that.
Yeah, but you can also you do that with GRB apply with the identity operator and a descriptor transpose. It's the same thing.
Yeah.
It's the same thing. So there would not have had to have been a GRB transpose. In fact, this is a very short function because all the things it needs to do, you will also see elsewhere. So the GRB transpose just puts these pieces together into the spec that you want for GraphBLAS, but it just simply calls all my internal methods that I need lots of other places anyway. So it's very Lego kind of building block sort of method. It's build up just these pieces. Okay. So I check the domains of for the cum mask phase. Things have to typecast properly. I check the dimensions to make sure they're okay, and if you can return an error if the dimensions mismatch. I always have the return a quick mask. That's if the mask is empty and complemented, then nothing happens, and I'm done. Okay. So otherwise, I'm now doing the transpose, and it is a very classic procedure for many GRB methods. Is I don't directly compute the result in the output matrix C. I'll compute a temporary matrix first, called T, I often call it. And so have I shown you this thing right here, clear static header?
That doesn't ring a bell.
Okay, so what this is doing, I should mention it here then, this is a way of creating an empty matrix. This is my matrix struct. This is now statically allocated. I'm not going to pass this back to the user, so I don't have to malloc it. I'm trying to reduce the number of mallocs I do, so I don't want to malloc the header. So here I just assign it to a static. I made it a macro because there are cases in which if I'm using Rapid's memory manager and I want to pass this header to the GPU, then I do need to malloc it. So I had to make this a macro so it could handle both of those cases. So this could run into memory, but basically it just makes an empty header for the matrix. And now I handle, this is a very common thing. I handle my CSR CSC. So there's two matrices A and C. So you're doing C equals mask of accumulator equals A or A transposed, T, which is A or A transposed. Okay, but the input matrix A and the input output matrix C could be already in different, one by row, one by column. Okay, and you could also be asking for the transpose or not the transpose. So I can fold those together, and I can be now CSC agnostic. If I say, well, if the two orientations of the matrices are different, then I just have to negate transpose, and now the rest will work. Now I can pretend that everything is CSC, and now I'm doing or not doing the transpose. All right, so now I'm doing the transpose. This came originally from the descriptor here, but I may have to negate it if this is different. So this is part of this reducing the number of variants of that I need to handle. Okay, so you can be, this is this weird thing. You can tell GRB transpose not to transpose with the descriptor, which means do the transpose, right? That's what GRB transpose does. If you say GRB transpose C null null null, null null A null descriptor, that means do the transpose. Okay, but so this is now, if you say don't transpose, then it means a transpose. If you say double transpose, like transpose with the call and then transpose with the descriptor, then you are just making a copy of the matrix. So this is when you actually need to make a transpose. And I do it one of two ways. If there's no accumulator, then I'm going to compute T equals A transpose here with this method. And the type I want to put it into is the C type. because there's no accum operator. Otherwise, if there is an accum operator, I'm going to cast it this matrix T. I'm going to keep it in the type of A. I mean, this is the input matrix A, this is the output T, and I'll keep it in the type A. There's no typecasting because I'll let the operator do the as it needs to. We'll do any typecasting. But if I'm just moving it directly, I might as well cast at the same time into C. Okay. So transpose cast is the workhorse method then. And then the alternate is, well, what happens if you're not doing anything? Like you call GRB transpose and you say with a descriptor transpose, that means don't transpose. So you're just doing an assignment really. So this takes constant time work. Basically, I make a pure shallow copy of the input matrix. So there I've got my transpose matrix. I either transpose it or I don't. And then I use the accum mask thing. And this is doing this. That's a whole nother kernel by itself. It's probably, so the transpose is 1500 lines of code. The mask is also 1500. It's big. It's 1500 lines of code. This is the accum mask process. And it's actually in some sense bigger than this because it calls things like GB add phase here. It calls some stuff from the EY's add because there's a very similar determination of the parallelism is add phase 0. This is the same thing because you're in the accum, you're doing an EY's add. But it's different because there's also a mask. So the mask operation is a little different, but the parallelization is the same as an add for the mask phase. Okay, so the mask is complicated. So I'm just calling out here now, and I always go through the mask. Now it may decide that it can do the accum mask can do a lot of short circuiting. It can decide, oh, there's no accumulator. Oh, there's no mask. So it's C equals T. So it just moves the matrix, moves the data from C into T, and we're done. So it can take order one time to do this last step. And that's the greased lightning path. If you just want to transpose the matrix and no mask, you don't do any work here in this accum mask. But this is a common setup for all of the GRB methods. They'll very often construct a temporary matrix and then move it into the accum mask phase. Apply will do that as well, I think. If you look at apply, we did do apply already. It also can call the accum mask, I believe. Yeah, there it is. At the very end of the day, we did GB apply. This was a little bit different. No, it varies. There it is, always at the very bottom. Except, see, there's some cases, oh wait, I've already done it. Yes, this is a short circuit that I've already done the entire work in apply, and I can bypass the final step because the C matrix is now done. And that's only done in very special cases, but that saves a lot of work. Okay, so this is the transpose. Now let's look at I don't think I've shown you some of these helper functions like GB shallow copy, for instance.
Yeah, we haven't
But
talked about shallow copying too much.
oh, we haven't talked about shallows. Okay, well we could do that here. I think that's a useful thing because shallow copies are used lots of places.
Yeah, it's come
I
up, but
think
we haven't given the details.
it's used in select. It's used in transpose. It's a full shallow copy of a matrix, purely shallow matrix. So there's other matrices which are half shallow and half allocated themselves. But let's look at transpose cast next. This is, let's say we're doing an actual transpose. Okay. So GB transpose cast, very short method. It says the let's see, what does it do here? The first thing it does is it picks an operator. The operator might be the one. It's a unary op. No, I have an internal operator. It's just called operator, but it's any operator. But I believe this is a unary op. Let's see. Yeah, it's a unary operator of a certain type. It's the one operator. It returns a one all the time. But that only happens if I'm doing an ISO output. So I'm doing C equals op of a transpose, but the op is one. And so I'm going to do the typecast, but it's just going to be a scalar. And null means don't use an operator. You're just typecasting. So I use internally, I'll use the typecast mechanisms I have. So the workhorse is GB transpose. So that's the big one. And I'll get to some of those nuances about this ISO 1 business later. I don't even think we'll see that in GRB transpose. I think it'll be, yeah, it's false. So we're not needing that yet. I'll use that elsewhere. Okay, this is 1,000 lines. This is a big beast. Okay, this is the workhorse transposing, and what it's doing here is either a transpose or apply an operator in a transpose, and it's also doing typecasting. And this method is going to call some other methods that'll do some of the work, like but this itself is not JITted. It's going to call other kernels that do get JITted, but it will call the builder, which I've not talked about yet, that GRB build, because some of the transposes, like transposing a hypersparse matrix, it's far faster to use just create the tuples and rebuild a matrix. There are two ways of using this method. You can transpose a matrix in place, or you can transpose a matrix from one matrix to another. And so I have a special case for this. And the sparse transpose cannot be done in place. So I'll make a temporary transpose and put it back into the from C to C, basically, if this is happening. Let's see. I've already talked about the idea of agnosticism. There are multiple methods depending on how I feel I can exploit parallelism better. And it's very much like a bucket sort. A transpose can be thought of as a bucket sort. Say you're transposing a row matrix, CSR matrix into a CSC, for instance, that's also a transpose, same thing, however you like to think of it. And your output is a bunch of buckets. It's like doing a histogram then. The problem with that method, though, is that who gets access to that bucket and do a parallel bucket insertion, right? That means atomics and so forth. That's not really highly scalable. And so I limit the use of that method for when I don't have many threads compared to the amount of buckets I have and so forth. And if I have too many threads, I'll use another method, the builder. Okay. All right, so how does this, what this method is doing? I've got my output matrix. I may be working on it in place. I have the desired type, and it may be different than the current matrix type of C. I have the format, which is it's agnostic, but I set this like at the very end. It's like, okay, who do you want to be? And then I set it in my method. So it just is it's just a flag to say, how do you like to think of this as matrix? Right now, I don't care. It's just it's an array of, if it's a CSC, CSR matrix, it's the same data structure. I don't care. So it's just a flag that gets set at the very end. So now I have the input matrix, and now I have, and this is oddly indented because this entire piece of 4 parameters describes what the operator, it's all related to the operator to do. I used to just pass in a unary op, but now I have a binary op with a bound scalar, for instance, or I have is it bind first or is it bind second? And do I need to reverse the row and column indices of this index unary operator? Is it ij or ji, right? Do I need to flip the I and j's? This is not a flip in the sense of a zombie. This is a like commutative flip. And that might happen if, remember, I'm now inside an algorithm which is CSR CSC agnostic, but if I'm applying an operator that cares about the indices, I have to know which one I'm doing. So I'll make this true or false if I need to. I'll make it pass in true if I need to revert this. And then there's my stack workspace for small little things. Okay. And so this is common kind of thing. I'll declare my variables at the front, because then if I have to have any failure, I can free those things even if they're not allocated yet. They're null, so nothing happens. And common assertions here of this is for debug only. And I determine if I'm doing a transpose in place or not right here. If I'm passing in A and C as the same matrix. Okay. And so I first need to decide which method to use. This is what this method is doing. I have to finish the input matrix if need be. So I will not have pending entries. I will not have zombies, but I could be jumbled. Or, but if it's a single vector, it's never jumbled. And that's actually important because I have a very fast method for transposing a vector. Now, you can't transpose a vector in GraphBLAS. Well, you can, yes, you can transpose an n-by-1 matrix and have a very special case for that that's extremely fast. Most of it's in place. You can do that very quickly, and not all in place, but I don't have to move the values around, for instance. I just can, I'll show you how I do that. So this is this important special case. And I did that, let's see. Trying to remember where that's needed. Some algorithms need that to transpose an n-by-1. Okay, so I get my input matrix. I decide, I get how my OpenMP context, like how many threads can I use? How big is the chunk size? You can set this in the context, and this gives me a granularity. This is a common thing across all my algorithms. You can change, and people don't tend to change this at all, but it sort of gives me a metric of how much work do you want each thread to do. The defaults seem to work fine. I haven't really tuned to the chunk size anyway, but that's doable. Okay. Now I determine the output type of C, and I also extract whatever information I need about the operator. And there's three kinds of operators. I got the unary operator, an index unary operator, or a binary operator that's bound to that scalar with the bind first, bind second. And so this just, decide what the types of the C matrix are. If it's a binary operator, and I assert here, some of these cases can't occur. For instance, a second operator with bind first, I will have removed that because that just becomes an identity operator, right? F of x, y, and x as a bound scalar, but it's a second operator. Wait, that's just, if I get that request, I'll say, oh, you just mean identity. So I've already remapped some of the operators. Now you haven't seen any operators from GRB transpose because there's no operator there. It's just a typecast. There's no operator in that case. The input op is null. We're only doing typecasting. Okay. And I have to look for positional operators. This is, if they are positional, it got really complicated. And so I decided I would just do the isotranspose and then apply the operator after the fact. It's not very ideal. Same thing with user index operators. I do the transpose and then I apply the operator in place. Okay. I determine here more about my operators so I can decide whether or not the so this is a function that is telling me if I apply this operator, maybe I should look at this. This is interesting, interesting function. Unup code ISO. I am going to determine what's happening to the output. Like you can have an input matrix with non-ISO valued, but when you transpose and apply operator, suddenly it becomes ISO valued. Or vice versa. You can have an ISO valued matrix, but when you transpose it and apply the operator, it could be a positional operator. So suddenly all the values are different. So you can go from ISO to non-ISO or ISO to ISO, or you can have all those 4 different cases. So let's actually look at, I think it's interesting to look at that GB UNOP thing. It's in ICE, there we go. It's this one right here. Let me look at this. So it's basically saying, okay, I'm about to apply an operator, potentially transposed. And I don't care whether it's transposed or not, actually, because this method doesn't care if A is transposed. I just want to know, is the output matrix C an iso-valued matrix? Okay, so we have an operator and we have bind first, bind second, and I get the operator code, which could be null, so the opcode is no op. There's no operator. If it's a positional, like an index unary op of some kind, well then the output can't be ISO valued. So C is not ISO. If it is the operators one or pair, which is the same operator, but one's unary and one's binary, then the output matrix is ISO valued and it's equal to 1. So that's a special case, ISO 1. And then if it's you can apply an operator that's a scalar, so you can replace so you can do first bin op with bind first, which is a useful thing to do. But what this says is C is first of X comma A is the operator. In other words, all the values of C will be equal to this scalar. You're putting in a scalar. You're making a transpose and you're changing all the values equal to a scalar. That's kind of handy to do, to be able to do. You can do that. And I support that as a built-in method. I could have done it in 2 steps. It'd be more expensive. So no, I have a special flag for that says, yes, C is ISO valued and it's the same as the scalar. That's the ISO S. Then now this will happen regardless if A is ISO valued or not. Now, what if A is ISO valued? Oh, if A is ISO valued, you have more options. And it depends on if A is ISO valued. I think up above, yeah, I've handled the positional cases. So even if A is ISO, C is not ISO. So now I don't have these positional operators anymore. I'm now down to A is ISO valued. So the C will be ISO valued now, but in what kind? Will it look like an A? Will it be a unary op applied to the scalar? So it'll be different, but it'll be it could be a different typecast, for instance. But it's either typecasted or apply an operator so this will help me to know, do I need to apply I'll need to apply the operator, and I do that down below when I handle ISO cases. So C is ISO if I return anything else but non ISO. I have an ISO valued matrix. So this is useful to know, because if it's ISO valued, then I'm going to build the values later outside the method. It's not parallel. It's just one scalar work. Okay, so now I go into selecting my different methods. Let's see. Yeah. So this is there's some parallelism here. Most of this, I'm just looking ahead so I can walk through. Yeah. All right. So now I'm actually going to do the transpose. 1, 2, 3, 4, 5 different cases. So we used 5 different variants, 5 different cases, and some of those will break into multiple subcases. So an empty matrix, well, that's easy. Build an empty matrix and I'm done. Bitmap in full. All right. That is an entirely different method. And I'm going to make a bitmapper full matrix. But I could do it really cheaply. Because if you have a scalar or a row or column vector, it's super cheap to transpose that thing. Because I can do it as shallow, right? It's like you're done. You transpose a dense matrix of n by 1 to get at it. A 1 by n dense matrix. Well, that's the same thing. Okay. And if there's no typecasting, that's just now it's going to be shallow. So I'm going to create a matrix, and what I'm going to do is I'm going to, where is it down below? I'll just do um, a a transplant if it's in place, or I will do a shallow copy, make a shallow copy. So this is really cheap. This is order 1 time in the cheap case. So that's really useful to be able to do. You can transpose an n by 1 dense matrix to an 1 by n dense matrix in order 1 time. Especially if it's in place, then there's nothing happening. You just tell me, oh yeah. And so it's a short circuit. So this is the short circuit. T equals A transpose. If it's cheap, okay, nothing to do. Otherwise, I've got work to do, and that's the transpose IX. And let's see, I have some transpose IX means transpose the there's no operator. What is transpose IX called? Why do I call it that? Let's see. I have these naming schemes. This is where I'm going to do oh, I just do it here. Okay, good. All right, so it's only here. Transpose. So this is the transpose the values and patterns of a matrix. That's what called IX, values and pattern. And there is yeah, there's no operator at all. So it's doing the work when there's no operator. I might be doing typecasting, but there's no operator. Otherwise, I call a method which has an operator. And this is 152 lines. And now I'm going to do the kernels and the JITs and all this. So I have GB transpose IX, which only appears here. I think there's just the one call. Transpose op is going to probably apply just in one place as well. Okay. But that's for the bitmap in full case. So let me, I think where did I call those in other places, don't I? Yeah, I'm gonna call these methods. This can handle the bitmap in full case, so can this. I'm gonna call these methods down below as well, but through other means like the transpose bucket or the transpose with the builder, I think. So the bucket, if you look for CGB transpose method, I'll pick the method and then I'll call the bucket, or I'll use builder directly, and there's the builder. Yeah. So, and the bucket will call the transpose IX or transpose op. The builder, yeah, the bucket will. So I'll use these 2 kinds of transposes elsewhere down below as well. Okay, so that's the dense case. Bitmapper full case. I have some possible cheap methods. Or okay, now I actually have to do the work. This is also cheap. I have one vector. So I'm transposing a column into a row. how did I get this column vector? Well, it could be a CSR matrix that's 1 by n. It's one vector in my data structure. That would be one vector, a matrix with one vector. Or it could be a CSC matrix of one column, or it could be a GRB vector, which is the same thing. So that's why I put column in quotes. I think of it as a column into a quote unquote row. And so this thing is now it's sparse. I've handled the bitmap in full case. Now it's sparse. And so I have to, let's see, allocate, let's see, the new row indices of a column because, let's see, and how do I fill them? Let's see. Yeah, I have to fill them in parallel because it's one row. So I have to put in all the row indices and everyone's in a new column. So there's some very simple kernel here to do this special case. So allocated a new matrix, allocate the P and the I array, and then potentially the numerical values, but I may do this shallow. I may decide I don't need to allocate this because this, I don't have to allocate it. I can just do a shallow copy potentially. Make TX be shallow. I'm not going to allocate the hypersparse. Create this. I'll do that. I'll do that below. I think. Do I do that below? Oh, I don't. Yeah, this is the cool trick. If it's okay, here's the trick. It's a sparse vector. It's not going to be hypersparse. When I do this, now the row indices of this data structure become the hypersparse column indices, the H array of this matrix. And then the row indices are all 0. Sorry, let's see. So now it's a hypersparse 1 by n matrix stored by column. So I have a bunch of row indices I have to store, but I have the column indices already. It's just the row indices of the input. And that's what this is. I just do the transplant. And if it's, so this is kind of unusual here. See, the input AI array is becoming the H array of the output, just like that, with no work to do. And the numerical values, though, have to be worked on. So I have to apply an operator to the numerical values, or I have to do a typecast of the numerical values from one matrix to the input matrix. I have a cast method, which I haven't talked about yet. Just does a typecasting. Or if I don't have to apply the operator, and if I don't have to do a typecasting, there's no work to do. It's just a shallow pointer. And it just either, if it's in place, nothing happens. If it was already shallow, it stays shallow. And so you can do an in-place transpose of a matrix with no work. Then if this happens, no work on the numerical values. So if you transpose a column vector in place, the numerical values don't care. They don't move anywhere. So you don't have to work on them. So it's much faster that way. Transpose has all these special cases because these are important. This is an important case. And then all I have to do is finalize this. And so what I'm going to get is a hypersparse 1 by n matrix. Okay, now I have, and it's hypersparse because otherwise, n could be large and I could have a vector of length 1 billion with 100 entries in it. Well, those 100 entries become 100 sparse columns in a hypersparse matrix. And the H array is the row indices of the column vector, which I now moved into a row vector. That's again, agnostically, everything is imaginally CSC. So when I say a vector this way, it's one vector. When I look at this, it's say 5 vectors. Of course, if everything is CSR, then just flip that meaning around. You're going from a row vector to a column vector, and then it's the same data structure. So then there is a little bitty parallel loop here to fill in this memory space. Now here's an example of a kernel. Then I don't need a JIT because all the indices are in 64. So if I ever do this in CUDA, well, I can't do this. I have to JIT the thing, right? This has to go through the CUDA JIT to do this copy. And then I would also, if I ever have, this method won't work if suddenly you see what's happening here. If those are different integer types, I can't do this. But they're all just int64, so it works just fine. So I can do the opposite. I can transpose a row into a column vector. And this is AV-len, it's maybe a misnomer here. It's one of the dimensions. So when I have a GRB sparse matrix, imagine if it's stored by column. The dimensions of that matrix is, well, dimensionally how many vectors there are. If it's hypersparse, it could be 2 to the 60s. It could be a big number. That's the dimension of this matrix, is the number of columns in the matrix, not how many are present. And then the length of those vectors is, again, a dimensional thing. It's not how many entries are in every row, or every column. It's the dimension. So there's these 2 dimensions. And one I call the vector dimension is the number of vectors. And then the vector length is the mathematical number of, the dimension of that vector. So it's in a CSC matrix, it's the number of rows. So if the vector length is 1, then it's already just one row. It's a row vector. It's an n by 1 matrix with a single row. So I'm transposing a row into a column. So I'm doing the opposite. And it's very similar to the other thing. I can do stuff like, I have to apply the operator. I have to, or do a typecast. So it's very similar. I can copy this. This is a copy of the code above, basically. And I have to compute the row indices of the output, and I might just be able to do it from the hypersparse. If A is an n 1 by n and stored in hypersparse form, the hypersparse list becomes the row indices of the output vector right here. So everything is done in place in constant time. So you go back and forth in place with this very, very easily. Otherwise, I got work to do. I've got to fill this in. And this, unfortunately, is, I should put a do here. This is not parallel. Oh, because I'm using one thread. I'm sorry. This is the sequential code. But this is what I'm doing. I have to flesh in. I have to find the non-empty vectors of A, which become entries in T. I've got to look to because see, if it's hypersparse, I know where I am. There's nothing to do then. But if the input matrix is sparse, I've got to fill in the row indices, and I do this in parallel. So I'm constructing the row indices of the output just in parallel. So it's not a, I mean, it's and it's a 2-phase process. If I wanted, I'm doing this in parallel. So I'm doing this computation. I'm going across all of the, so it's this 1 by n thing, okay, is it's sparse and it's stored by column. So the p array is of size n plus 1. And so, but I have to walk across those to find out, well, who of those vectors of length 1 is not empty. And if I find one that's not empty, then that's a new entry in the T matrix. Okay, and if I've decided to use a single thread, this is the computation to do. It's very simple. If I've decided that, oh, I've got a lot of work to do, well, I want to do this in parallel. So this loop right here is done in parallel with these 2 loops. So the first thing goes through in every thread. So it's a dynamic schedule. But this, I think, have you seen this GB partition thing before? I don't think we have.
We talked about it briefly.
We did. Okay. So all this is doing a uniform distribution of a space of this size. So it's basically, yeah, let me show you to again. Let's see. I think it's going to be, there it is. It's in the slice method. Okay. So all it is I want to, I have n things to do. And when I have that many threads to work on, it's this thread I'm using, and I want to take that and give this thread its work, start at K1 and go to K2 minus 1. So that's what it's doing. So I know where to start and where to end. So that's what this is doing. It's just taking, this is the total amount of work I do, which is AVDIM. And I'm doing it with this thread ID, which is decided up here, with this many tasks. So it's a very common, this you'll see lots of places. You just doing a n amount of work with n tasks, and have a task ID, and then just chop the work up uniformly. And that's what this task does then, from the start to the n minus 1. And so it does this. And now this right here just does the if test, but it just counts, just as the count. And then every thread knows, or every task, I call them tasks. They're not OpenMP tasks. This is my task loop. Okay, it's just a for loop. The ID is the task, my task, and then I may do this dynamic. I may do this. I could have done this statically scheduled because it's such a simple loop. But very often it'll be a dynamic, and it's one iteration. So a thread will grab an iteration, do a bunch of stuff, and then grab another iteration, do a bunch of stuff. And there's the count I've pre-allocated is the maximum number of tasks I would do. So this is, everyone's deciding, because see, you see what you're doing here is you're walking across an array and you're filling in an output array conditionally. So the first thing to do is everyone needs to know, every task needs to know how much work it's going to do. And then I got to know where to put it. So I do a cumulative sum. Now everybody knows where, every task knows where to put its stuff. Okay. And so that is going to happen. Then that gets the cumulative sum of the is overwritten by its, I'm sorry, the count is overwritten by its cumulative sum by this method. Then the next method repeats the work above, but it actually puts the stuff in its place. And where do I start? I start at where all the threads to the left of me, if you will, finish. And now, well, I own this part of the output, and let me put my stuff there. So that's a very common framework of doing, it's a lot of work to take this little tiny thing and blow it up into a parallel work. Okay, so and this is just, so still talking about one row. Okay, and that's it. Now I'm practically done. I've just had to fill in the row indices, and I'm done. And then this is a very common thing I'll do. It's like, did I get the right result? You see what this is this is the same algorithm, but just use a single thread. And just repeat the above algorithm sequentially. Like you look at this and you look up above, it's the same algorithm, but just don't fill in the array. Just say, whoops, oh yeah, I actually did just that. I've already done that assignment. So this is a very handy thing for me, a very common thing for me, that when I have a complicated, a little bit nutty kind of task like this to do, I'll just assert, oh yeah, I just did the right thing. Okay. Now we come to the general case. This is now this is 210 lines. Okay. Now we have the general case. The general case may use one of two methods. Okay. Either the bucket method or the builder method. So I have a thing called the and actually I'll have several places where I'll have a suffix method. It means what it's doing is I'm meta, I have a decision to make, and this one's actually quite big because there's a ton of assigned methods. I'll have a decision as to, oh, I have an algorithm I have to compute, I have a problem I need to solve, and I have 2 ways or 40 ways or 8 ways to do it. Pick one. Any one will work, but heuristically find the best one. And so the transpose method will look at this, and it's rather complicated. Heuristic. Okay. Because I have 2 ways of doing now. Now I've got a lot of work to do. I've got a general purpose transpose to do of a sparse matrix or hypersparse into another sparse or hypersparse output. And I want to do this in parallel. And I want to, and I'll probably find down here, I'll ask down here how many threads I'm doing. Yeah, I'll do the same thing. I'll say, well, how many threads do I have to do this with? And I think I actually have 3 methods, don't I? Yes, I have 3 different methods. I have a bucket method, I have a parallel bucket method, a parallel atomic bucket method, and then I have a builder method. So I'm actually picking between 3 methods. And I have the matrix I'm working on, and I'm going to return which method I'm going to use, and I'm going to also return uh, some decisions on the parallelization. And so that's what this is doing. And I don't know if I want to bore you with all the heuristics here, but first of all, if I have 2 threads or less, I'm going to use a non-atomic method. If I have more than that, but I have a lot of threads, I'll use atomic workspace. And now I'm going to choose between, do I use let's see, use the atomics method. I think I might just at the end of the day just decide, do we do the builder or not? Yeah, so this is deciding the bucket methods, will I do as atomics or not? And so that's what this whole thing is doing. And I basically look at the size of the problem here. I take the log of the number of non-zeros, and then I have this comparison to say, well, do I use atomics or not? Depends on the size of the problem. So this is from benchmarking, and depending on how sparse the matrix is, basically the M log is one of the dimensions. It's the log of one of the dimensions. Yeah. And so it's basically how many buckets I have. So if I'm putting like, I have a certain number of entries to put in a certain number of buckets. And so this will tell me whether or not I want to, if I have many buckets, I don't need atomic, or I can use atomic. So I have a few buckets. I think if I have very sparse matrices, I think the atomic method is better. The non-atomic method works better with many entries. Okay. But if I don't use atomics, I have to have more workspaces. So that's bad. So I make that decision for the bucket methods. There's 2 different bucketing methods. And then I have a third method, which is, well, do I use builder instead of anything I did above? I'll just do both decisions here. And this will make the decision of, well, when is the buckets, the work for the builder versus the work for the bucket, and use the builder if I think the work for the builder will be less than the work for the buckets, basically. And so it's, do I do a builder is doing an n log n, e log e. If e entries, I'll do an parallel e log e merge sort, in place merge sort. The bucket method is like e plus n here, and but I have atomics potentially, and the other ones is e log e. And so depending on who I think is better, I'll use that method. So this is a fairly complex heuristic, but it's quick to compute. So that's what I've done here. Am I using the builder? The builder is easy. Okay, using the builder, I'm basically, all I'm going to do is create a workspace for the, let's see, iWork. iWork is going to be used for um, uh, the row indices, which are the column indices of A. Let's see. So these are grabbing the, this is like converting my matrix to a tuple, it's like export tuples will do the same thing. Okay, if I look for export or extract tuples, I'm sorry. Extract value. It's actually, this method is in the tuple method. So extract tuples, all extract tuples does is it basically allocates some workspace and calls this method, right? So this is a method that's converting a sparse matrix into coordinate form. So that's what I'm doing here. I'm converting my input matrix into this workspace for the coordinate form. And now I've got my output matrix. Okay. And if it's in place, I don't need parts of my input matrix anymore. And if I can reuse the if I can reuse the row indices, if the matrix transpose in place, I've got the row indices of the input matrix. So I can recycle those. I can sort them in place, basically. So I glue on the column indices and then sort in place with the builder. And so otherwise I have to do some mem copies to get the, because I don't want to mangle my input matrix. So, and if it's ISO valued, I need to tell the builder that I have the scalar already. Don't do the, I may want to now apply an operator to the numerical values before I do any work. And otherwise there's typecasting going on. Then finally, I call builder, and there's a ton of ways to use this build. This is not the user API for builder. This is evil. And we haven't looked at the builder yet. Maybe we should have done the builder first. But the builder and the transpose talk to each other. This is then converting the coordinate form into a sparse form. So basically reverse the rows and column indices. So iWork here is been, and JWork is the workspace. This is the input triplets, and then this is the, the output matrix is T here. And there's lots of different, let's see, there's multiple ways I can pass in these indices. I can pass them in as a read-only array or arrays that I can consume into my output, and I'll do that to save some memory copies and some mallocs. But otherwise, the builder just constructs the coordinate form, and we haven't looked into that, so we'll do this. We'll do this later. Okay, so that's the builder form. I just set up the problem and I call build. But I do try to save some memory copies by doing short circuits. Like instead of the memory copy, I can sometimes use the matrix data in place and do an in-place build. So otherwise, now I have a very complicated method to do the bucket sort. Okay, so the builder is here, transpose with the builder. And where do I just think I call it just once? Yeah, just at one place. So this is one way to do the transpose. And if the matrix is hypersparse, I'll choose the builder method for sure. Because if I have a matrix 2 to the 60 by 2 to the 60, I would need 2 to the 60 buckets to transpose that thing. Because even if it's hypersparse, you don't know that you may have a column that's got two, well, it wouldn't have that many, but you don't know. I don't know what the max number of unique output columns is. And so I would just allocate one bucket per vector per dimension of the output. So that's expensive. There's too many buckets. If it's hypersparse transposed to hypersparse, I can't do that. And I won't. I will pick the builder method in that case. Because and that you can see transpose in that selection here. Do I use the bucket or do I use the builder method? Well, this is a double because it could cause integer overflow. The work for the bucket is dependent upon the number of entries I'm doing and the sum of the number of vectors, which is actually smaller than the dimension. This is the number of non-empty vectors. It's equal for the sparse case. This is different if they're hypersparse. Plus it's the dimension of the matrix, this dimension, because that's how many buckets I have to make. So that's 2 to the 60. This bucket work will be enormous. And the builder work is just E log E. It'll be much, much less. So I'll always use the builder if it's very hypersparse. Okay, so the bucket sort, the bucket transpose. Okay, and this is a parallel. Well, this is actually, there's now 3 different algorithms. You haven't seen the JIT yet. And we haven't seen the JIT here either. Because I will call, where will I do? I call another, yeah. So here's where the JITs will be in here, in these methods. Transpose IX and transpose op. Okay. So transpose bucket. Let's look at that. And otherwise, I'm done. Right. I think I'm almost done. Well, no, I'm not done. After I do the transpose, no matter how I do it, I may have delayed the application of the operator, like if it's positional, or if it's a user operator, I don't apply it. No, I'm sorry. It's a user index operator. It's too complicated. So to figure out how to do that. So I just did it later. I've not done it yet. So now I have to apply it to the numerical values that I just transposed. So I'll move the data and then I'll walk over them and replace it with the application of the unary operator in that case. And now I'm done. Now, when I'm done, this C matrix here, I call it the C matrix. It could be the temporary matrix of the, it wouldn't have to be the user's C matrix. It could be itself a different matrix, but whatever the matrix is, this is my output matrix. I have this notion of conform. So when I compute something, I compute a matrix, I'm done with it. I've built me a matrix, and now I decide, now wait a minute, that's not the best data format for this matrix. And so I give this matrix a chance to move, once I've built it, to move to what it would prefer. And that's the conform process. And I look at the matrix and I say, well, it's currently hypersparse, but you know what? It'd be more efficient to store this as sparse. Or, oh, this is sparse, but now because it's got so many entries in it, oh, well, let me make it bitmap. I'll make some heuristic decision like that. And it's got some hysteresis to it, that decision, because you don't want to just willy-nilly change a matrix if you don't have to. So if it's already in one format and it's decent, I'll just leave it. And so there's a bit of hysteresis to that. And you can, if this is the final output matrix, we'll have, you have control over this conforming process. Like I won't conform it into a format that is not permitted to me by the hints by GRB get or set, GRB set. Like, hey, matrix, you can be sparse or hypersparse, never bitmap or full. Okay, fine. The conform will limit myself to the ones you've told me that I can do. Okay, so that's this method here on the left. And the only thing left here is this, where is it? The bucket. So this is the bucket method, and it's the transpose bucket. This is 347 lines of code. So, but it's no JITs yet. Well, that'll be later. Okay, so I get the size, get the number of threads to use. build myself. This is doing the actual work now, constructing a new matrix. This is, where is it? This is the output, but it's not the user's output matrix anymore. It's always going to be some temporary matrix with a static header. And I actually probably assert that somewhere. Assert that C is not null, and also assert that either the header is static. I have a flag inside my matrix to say, is this a statically allocated header? And then I have, or I don't allow those. So it's a static header in general, unless I'm using the GPU, then it's not. I'm going to be creating some workspace, and this could be fairly big. So I'm allocate the content to the matrix and its dimensions. And then I create some workspaces, but I have an array of workspaces. Each workspace has a certain size for that thread. So now I've decided, I think in the method, or in the transpose method, I will have decided how many workspaces I need. In the non-atomic bucket method, every thread needs its own buckets. That's expensive. But I allocate that space here if it's worth it. And sometimes it's worth it to do that. If I have 4 threads, that's not so bad. Every thread is every workspace is pretty big. It's this length of the number of buckets. Okay, so it's big. Okay. Now I'm going to do one of its 3 methods. Yeah, there's 3 methods here I'm doing for the buckets. Again, they're all bucket transposes. The first thing I do is, let's see. Let's see. Is the counting. Yeah, so the first phase is counting how big the buckets are, how big every column is going to be. And so this is single threaded. It's really simple. Go through entries. It's just basically a row count and cumulative sum, and that's my column pointer. So I'm computing the column pointer. Phase 1 is the symbolic analysis. And so this is what all the methods below are going to do. They're going to do a count, do a cum sum, and that gives me the CP array. Okay. So if I have 1 workspace, then it's the atomic. And these counts are going to be applied atomically. So I'll basically have a version of this method where all the threads are going to share the workspace, but you can see down here, it's going to be done with an atomic update. So the analysis is very similar to the sequential phase, except it's just now parallel. But the plus here is done atomically. And still the cum sum and the mem copy. Okay, the non-atomic method, every thread has its own workspace. And so every thread does its own local count of how many entries are every row. And then I do a cumulative sum across every the original number of threads up above, and every row gets its own cumulative sum, and that's the final output there. So there's no atomics needed here, but I need lots of workspace to do this. So this is expensive in terms of memory, but it's faster if I only have a handful of threads. And then I do the cum sum, and now I have to reset my workspaces because I'm about to use them here. So now finally I do the numerical values to fill in these buckets. All I have is the CP rate. Now I need to fill these things in. Okay, so this is now GB transpose. transpose IX. I have to fill in the row, and I call it IX because I filled in the P array already in the symbolic analysis of the method. I've already filled in, computed the column pointers of the output matrix. Now I need to fill in the row and column indices. This also does the full and bitmap cases though, directly, because there is no workspaces, there is no CP array. It just does it directly. But the sparse or hypersparse case, the column pointers CP are already computed on input, but the hyperlist, let's see. I think C is not going to be sparse on output. I think it's going to be, or hypersparse. I think it's always going to be sparse. I'm not sure. I'll have to look as I go down. There's no CP array, so I haven't here. I've computed it, but for these two cases, I don't need that. I call these methods, if you notice, if you remember from GB transpose, I called these directly in the full or bitmap case. I called these directly, and the workspaces will be none. There was nulls passed in for the workspaces. Okay, so ISO is a special case, which it's not JITted. I don't need to JIT it because the numerical values are just a single typecast. Okay, because this method doesn't handle any operator. It's just doing typecasting. So if the output matrix is ISO valued, I just do the typecast and then I have to transpose the pattern. Okay, otherwise, I will try the factory kernel, and I have 100 and what is 13 squared? Okay, because it's going to do typecasting. So I have a lot of different transposes happening here. If that fails, I try the JIT right here. And if that fails, I try the generic kernel and I'm done. And so this is the transpose I'm doing. It's the transpose template. Now I'm into the templating methods. Transpose template is also used inside this kernel here for the factory. If I go to the unary op tran, let's see, where is it? Factory kernels. If I go to here, I don't know, this is square root. So you're transposing and doing a square root of a complex float matrix. Okay. And that's this method right here. It's the same, although, sorry, there's no operator here. What's the, oh, right. The operator's identity. Sorry, I'm in the wrong place. You see, look at the mixes of types. There, if you look at there's like, no, there's like all pairs. Like 13 squared of these, 169 of these. And they're all say, let's just pick this one, identity, but and these are factor kernels. So I have to hard code in, this is, the Z type, output type is UN64, the input type is IN32. And the operator is a typecast. And so I'm going to call, again, I'll just call the transpose template now is doing my work. So let's look at the transpose, and now it's the fully templatized source transpose. That's 1 o'clock. Okay, I'm good. Transpose of, let's see, template. So here's my templating methods, templated methods. Okay, transpose template. The transpose template is, it's not a function, it's just a piece of code. It just starts with a curly bracket. Okay. Let's see, bind first or bind second. I forget what I'm doing here. But I have to get the pointers to the numerical values for A and C because I have to work with those. And then these different templates are going to do the 3 different algorithms, and the transpose sparse is going to have those different bucketing algorithms inside of it that I now am actually picking at runtime. I could JIT, when I JIT this, I could make this probably more terse code, but this is what I had before the JIT. So if I'm in the JIT kernel, I know the format of the matrices at compile time. If I'm not in the JIT, I have to look at it at runtime and whether the matrix is full, bitmap, or sparse. Now here the input is sparse or hypersparse. The output is never hypersparse. I'm building a sparse output matrix. So, you know, it's going to those one per bucket, right? And for the dimensions of the matrix. So that's the 3 different algorithms. So let's look at the bitmap and full or simple. Okay, the bitmap is just silly. In fact, I don't. This is the bitmap case. This is a bitmap transpose. And I basically partitioning across the whole matrix. I do the mod and div to figure out where I am, and I apply the operator. And I, you know, where I'm in A and where I'm in C is different. And so this is not really very fast, but it's very simple. If I look at the full case, I'm only doing the numerical values anyway. This is the full case. Just iterating through all the entries, you know, Cij equals AJI with an operator. The tricky part here that I'm not doing very efficiently is that the you know, I'm taking mods and divs and I'm iterating nicely through the output matrix, but I'm bouncing around badly through the input matrix. I really need to do this by tiles, if you will, like break it up and do sub matrices, and I'm not doing that. So this is not a very fast transpose. But then I don't ever typically have to transpose big dense matrices anyway. So I haven't bothered. So those are very simple algorithms, the bitmap and full case. The transpose case is where I have again, it's still the bucketing. It's not the builder. They're both, but I have 3 methods here, just like we had 3 methods in the, where was it? Was it the 3 methods were here? No. GB transpose, I think. No, it was, where was it? It was transpose bucket. That's what I'm looking for. GB transpose bucket. You see, I've done the 3. I figured out. I'm already picked the bucketing method. But am I bucketing with a single thread? That's easy. Am I bucketing with atomics? Okay, it looks like that. With one workspace. Am I bucketing with non-atomics, which means I need lots of workspaces, 1 per thread? And then I call this method, but in this method, I'm going to go back again to 1, 2, or 3 for variance. Okay, so let's compare. Let's look at this. The sequential case is easy. A transpose is actually very simple, single threaded. You have to do the row counts. Like imagine A is stored by column and you're constructing a C matrix. Essentially, it's like it's stored by row. So you have to count, go through the A matrix and count every row. How many entries are in a row of the, and that's the output. Then you cum sum that, and that gives you the number of, you know, that gives you the CP array of the output. So this is a symbolic phase 1, symbolic analysis, and it does not depend on the data type, does not depend on typecasting or the operator or anything. Now I need to also do this for the numerical values and the actual, I need to fill in the row indices and put it in the bucket. So basically it's Cj equals Aij with an operator applied. So there's a single workspace and that is this one. And I figure out, you know, where I am in this sparse matrix. It could be hypersparse. And so A could be hypersparse. It's the kth vector, but it's in vector J. And that becomes the row index of the output. that's a bucket right there. Where? Well, in this position. And so I'm filling in every, if you think of C as a CSR matrix now and A as a CSC matrix, I'm filling in every row, one entry at a time. And so every, if you will, every row of the output matrix C of the CSR matrix, if you want to think of it that way, is its own bucket. And this just advances. So the single threaded case is very simple. Although it is applying an operator, unless it's an isotranspose, in which case I don't need to construct the output numerical values. So I skip this, and I know that at compile time. Okay, atomics looks just the same, except it's an atomic. This thing right here is called an atomic capture increment. It's doing workspace of I++, and then give me the value before it was incremented. It's called an atomic capture increment. And in OpenMP, I have to hide this stupid things behind macros because Microsoft compiler is brain dead. It doesn't support all the atomics I need. And so I have to use, it's very annoying. I have to have this kind of ugliness. Do I have an atomics? Let's see. Atomic. Where do I have this? Kernel shared dimensions. Let's see. I think I might actually do it here. OMP. Yeah, it's OMP. GB atomics. There we go. Yeah, OpenMP. That's where I have OpenMP. So atomics. OpenMP4 is very simple. The pragmas sometimes are different depending on the version of OpenMP. Atomic reads and writes are pretty simple. Atomic flush, if you have it. Atomic capture. Okay. Fine. Just say atomic capture if you're OpenMP. But if you have, let's see. Yeah, this is, if you're the dumbest compiler on the planet, then call your special thingy. Otherwise, it's just an OpenMP. Simple, right? I mean, I could have put that right here. Right? And it would, oh, this is a capture int 64, a capture increment. Where is it? Capture inc. It's capture inc. Capture an increment. Yeah, capture post increment. There we go. This is what it looks like in normal OpenMP. It's very simple. There's just a pragma and plus plus. So it could be very simple here. It look like this line of code, literally. But if you're a brain dead compiler, namely Microsoft Visual Studio, you have to use this stupid thing because they don't support OpenMP very well. Yeah, so that's the atomics. Atomics are slower, but then I only have to have one workspace, and it's a direct map over from the sequential method. It's very simple. But if you have, just a handful of buckets and lots of threads, and maybe the number of buckets is small, maybe you have 10 buckets, maybe the output matrix has 10 rows, right? If you think of a CSR to CSM matrix, you might have 10 buckets. So there's gonna be a lot of contention on those atomics. So I'll use an non-atomic method. Every thread has its own workspace, and then I don't have to use atomics. This kernel is also very simple because every thread gets its own workspace, and I've already done the cum sums across those perfectly. And so I know every thread has its own position inside every bucket that it keeps track of independently. And so there's no contention, but then you need a lot of space for the a lot of workspace, because it's number of buckets times the number of threads is the amount of workspace you need. And if the number of buckets is the dimension of the matrix, if you have 32 threads, right? That's 32 n space for transposing an n by n matrix. That's a lot of memory. So I wouldn't use this method. I'd either use the builder, or if n is big and you have 32 threads, I would probably, and I decided to use the bucket method, I'd probably use this instead. And there's not going to be much contention, because if n is big, a million, say 32 times a million, that's a lot of workspace. Oh, but if it's a million with one shared workspace, then there's not going to be much conflict over the atomics. Now, one thing that's interesting though about this atomic method is it produces an output matrix that is now jumbled, because all the threads are just sticking their things in the buckets. There's no guarantee that that they'll put it in the right order. It's just an atomic increment. So different threads will come in and it'll be jumbled up order. I think the non-atomic method will ensure sortedness on the output. The bucket is like a bucket sort. I mean, the bucket transpose is very much like a bucket sort. So this will, I think the output for this method will, these indices will appear in sorted order. And the same thing with this one, with the single threaded method. But if there's a single workspace with multiple threads, the output will be flagged as jumbled, because you run it again, you get a different answer. You get a different order on the output. So there's a downside to that. You may have to sort them. So that's the bucket transpose, 3 different methods. And really, I could also, this and this test, 3 different methods. I could, the JIT could this could be known at compile time, but I didn't. I just left it as runtime because that's my factory kernels were already working. I didn't change that. Okay. So that is the transpose bucket method. Let's see, where have I gotten to? With this IX, but there's also transpose op to apply an operator. Now it's going to use these same kernels. The apply will be actually apply an operator. These 2 methods are very similar. Transpose and apply operator. If you look at this method, and if you look at GB transpose IX, which does not apply an operator, it just has typecasting. Make these bigger. Here we go. There's a lot of similarities between these 2. Here, instead of typecast, the ISO case will apply an operator, and then just it's the same algorithm. I could have, this thing, if it's a unary op, I'll have a unary op transpose, but now this is a general operator like square root or something. Whereas over here, it's a typecast, and the factory is different. This is a type by type switch case. Input type, output type. So it's 169 variants, something like that, 13 squared, not including user-defined types, I think, or maybe just one identity for that as a mem copy, I believe. No, there's no factories for the user-defined type, sorry. This is 1 per operator with no typecasting. And so again, the JITs will be different. This is well, actually, this is the same JIT here, but here the operator is just passed in as the identity operator for the JIT. Otherwise, it's the same. That's actually calling the same method. The JIT's the same at the end of the day, and the generic is slightly different. The generic over here, to apply, it does a cast. To here, I have to do an operator and a cast potentially. And then here, it's bind op. It's a binary op bound to a scalar, and that calls the factories as well. The binary op factory. And it does it again for if it's bind first, bind second. This is the bind second factory case. The bind second method. So every, otherwise it's using the same templates. Internally, it's all down to the same 3 bucket methods or the bitmap method or the full method. It's just that how do you define the operator? It's going to be different. Is it a binary operator, bind first, bind second? And where do I find it in the, if I go to the factory kernels, where's all my binary operators? Oh, it's EYs. Yeah, I just put them in EYs, I think. Like here's plus. I think I have a bind. Yeah, here we go. So this is float 16. Okay, so I have a, this is apply. Yeah, here's my transpose. So here's a transpose of bind first with the plus operator bound to a scalar, and it's the first parameter. And there's this input scalar, and then there's the transpose template all over again. And applying the operator is now applying it a binary operator, but otherwise it's the same algorithm. So that's the factory case, and the JIT cases are actually, I guess they're different. This is a unop JIT. I think I have a transpose binop JIT. Source JIT kernels. Oh. Yeah, see I have 3 JIT kernels for transpose with bind first, transpose with bind second, and transpose with the unary operator. Including that case, it also does the typecasting for me. Okay, so so if I look at the transpose, the GB transpose op, I think this is gonna, yeah, this is gonna call the JIT, either the unary op JIT or the bind first JIT or the bind second JIT, basically depending on which variant I'm at. And so this method here, basically this transpose and apply operator, it's going through these multiple cases. It's going through the ISO case. It's going through the unary op case with the unary op factory. If that fails, it uses the unary op JIT for the transpose, or if that fails, it uses the generic kernel for the unary op. And there's the unary op right there, function pointer. Or, oh, it's a binary op bound to some scalar. Okay, let's get the scalar, do typecastings of the scalars if need be, and now we know it's a bind first. Okay, do the factory, 3 different, multiple factories for the binary op, and if that fails, use the bind first JIT, which is different than the bind second JIT. I guess I JITted them differently. I could have. Why did I do it that way? I don't remember. It was just simpler. I think it mimics how it was simpler because it just mimics the structure I had already for these factory kernels. Like, oh, factory fails, use a JIT. And for some reason, it decided that the bind first and bind second JITs were different. That's interesting. Why would I have done that? JIT kernels, JIT. No, JIT wrappers. Let's see, go to the JIT wrappers. How do they differ? They use different, they're almost identical. Let's see, transbind first, transbind second. Let's see, JIT kernels, where was it? Template, yeah, diff. Let's see how these are probably very similar. Yeah, they're very similar. I guess, yeah, they're different. It was difficult. Yeah, there are different typecastings going on. And how I applied the operator was different. Yeah. So I made it as separate. I made them separate JIT wrappers. Yeah. Yeah. That's why, because of how the operators are defined and called. It's different. And where the scalar goes is different. Let's see. But at the end of the day, you see, this is a generic, for instance, right here, this is a generic kernel, bind op bin first, bind first is true. So it's applying a binary operator and doing a transpose, and it's applying a binary operator in this way with a scalar bound to the first input. Okay. But then at the end of the day, I pull in my template. And this is how I get the operator there, and I'm done. And that the transpose template, see, it's on all these different places. It's in the, it's used multiple places. It's used inside the JIT kernel. It's in the code generator, which generates the code for the factory kernels. It's inside the bind first and the bind second and the unary op, and it's also inside this is, I think, the bitmap for full cases, and so is this. I can't recall. So this template gets used everywhere. Transpose template. So this thing right here, this three-way method, or this is not the three-way method. This template gets used everywhere, and it's being used for the full case, the bitmap case, or the sparse case, which is 3 different algorithms. So it's this all-to-all kind of thing. I have these like 5 different algorithms here. Full case, the bitmap case, the 3 sparse cases, all doing bucket transpose for the sparse case. Those 5 algorithms are married to, or joined here to this version, or this method calls all 5, or the JIT uses all 5, just with a different definition of the operator. So there's a lot of, but you see, you don't see the algorithm here for the transpose. I don't need to, because it's all hidden inside this template. So this is a very common structure. You've seen it with the apply, right? You see code like this about doing the factories, doing the JITs, and so forth. You don't see the transpose algorithm because that's in the template. You see all the setup. You see things like determining the sizes, the types, and maybe doing some typecasting and deciding, you know, maybe casting a scalar to pass in, maybe doing some parallel analysis, like how many workspaces am I going to have, slice the input matrix for parallelism, which I only have to do once, not for every JIT kernel, because it's always going to be the same. But you don't see the actual algorithm, you just see the reference to the templated algorithm here and here. And if you looked inside this, we saw it there inside the JIT kernel. That will eventually compile a code that pulls in this template, which is now known at compile time, what the format is. So it doesn't actually building all 5 algorithms, just one here, or 3 here, because they're all combined into one selection at runtime. Okay, so what else? So the actual code that gets templatized is very short. It's a very simple algorithm. At the end of the day, there's all this machinery around it to get it to do all its different variants. And the reason there's so many is because I don't want to just transpose. I want to simultaneously transpose, because I'm moving the data. I don't want to move it and I'll then apply an operator later. I might as well just move it once. And the reason I did that is because apply with transpose or apply and typecast, which is like an operator, applying an operator. So it's like an apply with transpose. Happens all over the place. Like if I have to transpose a matrix, I might as well also typecast it to the needed type later on. Why cast it later? If I'm going to move the data, make a copy, it's a temporary copy, I might as well also typecast it, because that's a very expensive operation. I don't want to move over the data twice. So I made I could have made the transpose just not apply any operator, just do the transpose and leave the types the same. Just move, do a mem copy literally of the data, input to output. Don't typecast, don't apply an operator, don't do anything. But then when I'm done, what would I have? Oh, I have to apply an operator. Oh, I have to typecast. You see, and that would be more memory traffic. So as a result, I have all these different variants that are variations because I want to insert the operator into these kernels. And I did these variations before I did the JIT as well. So I have them, different factories to do the different cases, because the transpose is such an important method and very costly method. So I'm trying to fuse as much as I can, if you will. So that is, I think, that is everything here. That is a transpose. You saw the user interface to transpose. You saw picking the method. You saw the transpose casting, transpose in place. Let's see, what does that do? I don't know if you saw this one. Oh, that's easy. That's a one-liner. Transpose in place. I pass in C equals transpose of C with no operator. Never mind. That's pretty simple. Transpose cast, I think, was also a one-liner. Yeah. Pick an operator. And then do the call transpose. And you saw in the the biggest amount of work here. Yeah, the biggest file was this GB transpose right here. This was this large method which did all the different variants. It decided, am I going to use the builder? Am I going to use the bucket? Am I going to use the special case for one vector row or column? Which those did not need a JIT, because they can just do typecasting now, or they can just do apply an operator to a matrix. Now that itself gets JITted. It's just like an apply. I think like, you see, I call apply an operator. Where does that come from? Oh, that's in the apply method. That's here. And that's going to call its own JIT that applies an operator to a array, not a GRB matrix. It's just a work array, so I can use it in other places. So the GB apply app does get used quite a bit in other places. We did apply last time or before, and you see it's used in several places. It's used within apply itself. It's used within, yeah, there's apply. Okay, but it's also used in row and column scaling and in transpose. This is part of matrix multiply. This is multiplying by, this is like multiplying by A times the diagonal on the right. If it's stored by column, you're scaling every column. Or this is doing D times A, where D is a diagonal matrix. You're scaling every row. And you just have to apply the times operator of the summit ring. And that's what these two things do. So apply up gets used a lot, and it's using the transpose now, but you also see the apply using the transpose. Where is it? No, GB transpose. Right here. Because this is the top level apply. We did apply last time, but this is interesting. Let me take a look at this. GRB apply eventually calls GB apply right here, GB apply, bind first, bind second, and so forth. And that just also calls GB apply. And GB apply is deciding what to do. It's checking the inputs, blah, blah, blah. And it might decide, well, I'm also needing a transpose. Oh, okay. If I have to transpose it, it's a transposed apply. So call the transpose. I can apply the operator at the same I do the transpose. So it's the same thing. It now shifts over to transpose. We go to transpose, and transpose might decide to say, hey, apply, could you please apply? They talk to each other. To apply an operator to an array. And that's over back to you, apply. Apply says, here, transpose, it's yours. And transpose says, yes, great, I'll do it. But wait, I need to apply an operator. Could you please do it for me? Sure. And that's done with apply op, which is here, which says, oh, sure, I'll do it for you. Where is it? Yeah, right here. But GB apply op doesn't talk back to transpose because it only works on arrays. We already did this method. So whoops. So it's whoops, get status. I don't want to delete anything. Yeah. So this is a very common setup, a very common thing in SuiteSparse. It's it's all linear algebra. Every method is like relying on every other method almost. So the call, if you look at the call tree of GraphBLAS, is which method inside SuiteSparse GraphBLAS, what functions call what functions, and you try to draw a plot of that. It's a rat's nest. And it's not a rat's nest because I don't know what I'm doing. It's a rat's nest because it's linear algebra. And everybody likes to talk to everybody else because it's all kind of plug and play. It's actually a good thing. Think of it as a dense matrix. Fine. It's a very simple thing. Don't think of it as a graph of which, right? If you think of a modular piece of code, it's like, well, you have this thing over here, it does this thing over here, maybe some helper functions down at the bottom, but you shouldn't have everything calling everything. Well, in some applications, that's a logical design where you have very strict walls of separation. This is linear algebra. Everything wants to talk to everything. Reducing a matrix to a vector is just a matrix vector transpose. So I call it from there. Everything likes to talk to. So the apply and the transpose are joined at the hip like this. Then as a result. Okay, where are we? I think that's transpose.
Great.
I think we're
Yeah.
done.
We got about,
Well,
we
we
do take
got
a 20-minute break because we got that LA graph
the
meeting
LA graph
coming
meeting
up.
is coming up.
Yeah.
Yeah, I need a break.
I'll go ahead and stop recording.